Today, I will introduce our ICASSP paper, Partially Fake Audio Detection by Self-Attention-Based Fake Span Discovery. Today's presentation is divided into 5 parts: motivation, background, proposed method, experiment, and the conclusion. Here is today's motivation. The significant advances in speech synthesis and voice conversion technologies can undermine the robustness of speaker verification models. The ASV spoof challenge arouses the attention of fostering spoofing speech detection research. However, they didn't consider partially fake audio into consideration. The first audio deep synthesis detection challenge, ADD 2022, extends the attack scenarios to the partially fake audio detection task, which is a brand new scenario. However, such brand new attacks haven't been studied yet. So in this work, we propose a novel method to tackle it. Now let's get into the background. Firstly, let's talk about what is automatic speaker verification. Given an utterance, the ASV model will compare it with the enrolled speakers and decide whether to accept it or reject it. However, some attackers can use recording, speech synthesis, or voice conversion methods to generate fake audios, which are very similar to the user's speech, and even humans cannot distinguish the fake one from the real ones. And the fake audios will be used to deceive the ASV model. That's why we need anti-spoofing models to tackle such attacks. And due to recent efforts, a lot of high-performance anti-spoofing models have been proposed. But another kind of spoofing attacks, partially fake audios, haven't been studied yet. Let's look at what is partially fake audio. Given a piece of real speech produced by human, a text-to-speech model will generate a piece of fake audio. Then a part of the fake audio will be clipped and added into the real one to generate partially fake speech. Only a part of the speech is fake, thus the partially fake audio is even more stealthy and dangerous. The text-to-speech here can be replaced by recording and voice conversion. Let's get into the proposed method. I will firstly talk about the rationales. In this work, we introduce a proxy task named question answering or fake span discovery, in which the model has to answer where is the fake clip in a piece of partially fake audio. As a result, the proposed anti-spoofing model has to predict not only whether the input utterance is real or fake, but also output the start and the end of each fake region. In this slide, I will introduce the extraction-based question answering strategy, and then I will show the details of the entire structure. Here is the question answering strategy. Given a sequence of embeddings extracted by the first few layers of anti-spoofing models, H1 to HT, suppose HS denotes the start of the fake audio frame and the HE is the end of the fake audio frame. Then we feed this H sequence into the feed-forward layer. We want the NN to predict the start and the end point of the fake audio. We can see the sequence of A vectors have two dimensions. The first dimension denotes how likely the frame is the start of the fake audio, and the second dimension denotes how likely the frame is the end of the fake sequence. You may notice that this is very similar to extraction-based question answering. Actually, this work is inspired by extraction-based question answering. We want the model to learn to find the start and the end of the fake region during training. Here is the entire pipeline. Given the input sequence x1 to xt, the SENet will extract the hidden embeddings z1 to zt. The SENet is shown in this table, and the Z sequence is fed into the self-attention layer to get H1 to HT. Based on the H sequence, we have the following two blocks, the question answering block and the anti-spoofing block. I have introduced the question answering block in the previous slides, and the anti-spoofing block conducts binary classification to predict whether the input utterance is real or fake. Now let's get into the experiments. During the training phase for constructing fake audios, we generate the partially fake audios by inserting a clip of audio into the real audios. The inserted clips are derived from three parts. Firstly, fake audios in the training and the development set. Secondly, real audios other than the victim audio in the training and the development set. And lastly, audios resynthesized by the traditional vocoders, including Griffin Lim and the Word, based on the real audios in the training and the development sets. And as for the validation set, we use the adaptation set consisting of partially fake audios synthesized by ADD 2022 for model selection. About the experimental setup, most of the input features in this paper are male spectrograms with hop size of 128 and the output bin size 80. We perform on-the-fly data augmentation by adding noise from Nielsen dataset, adopting room impulse response, and applying codec algorithm. Let's look at the experimental results. I want to raise that the models trained without the question answering strategy attain the equal rate of around 40%, which indicates that such models without question answering strategy cannot distinguish the partially fake audios from the genuine ones. And then I want to verify the effectiveness of the self-attention layer. The self-attention layer is one layer of transformer layer. In the two settings with FFT window size of 384 and 768, the improvements after adding self-attention are significant. And the other settings are with the same trend. Therefore, the models with self-attention will be adopted for the following experiments. This table exhausts the experimental settings under 4 different window sizes, 3 pooling methods, whether to use data augmentation, and whether to use the resynthesis data. We have the following observations. Firstly, the equal error rate are improved with the help of data augmentation in most of the settings. And secondly, enlarging the training set by the resynthesized data will benefit the equal error rates when data augmentation is conducted. And then lastly, the SAP and the ASP pooling strategies greatly improve the equal error rates when both data resynthesis and augmentation are applied. To increase the diversity of models in the fusion stage, MFCC, LFCC, and SyncNet are further taken as input features. We fix the FFT size as 384, apply only ASP pooling, adopt data augmentation, and the resynthesized data due to limited computing resources. And the average fusion of the top 5 models achieves the best equal error rate of 7.9% and ranks the second in the partially fake audio detection track. Finally, we have the following conclusions. Inspired by extraction-based question answering, this paper proposes a self-attention-based fixed band discovery strategy for partially fake audio detection. The proposed strategy lets the model to predict the start and the end position of the fixed clip and address the attention of the model into discovering the fixed band. The final submission achieves 7.9% equal error rate and ranked the second in the partially fake audio detection track of ADD 2022. Our future work will explore the proposed strategy by adopting other backbone models and the front-end features. That's all I have today. Thank you.